to Splice Institute 2021. This is our opening night presentation led by our featured guest composer, Carla Scaletti. We are really excited to have Carla here with us all week. She works on the Kyma system. She is an experimental composer, has designed the Kyma sound system, and co-founded the Symbolic Sound Corporation. This is our opening night. Her compositions always begin with a what-if hypothesis and involve live electronics interacting with acoustic sources and environments. She was the winner of the 2017 SEAMUS Award for important contributions to the field of electroacoustic music, and she has been invited to present keynote addresses at the International Conference on Auditory Displays and the International Computer Music Conference of 2015, and was an invited participant in the GVA Sessions of 2015 as well. And so we're really, really psyched to have her here. Please write all of your questions in the comments. I'll be monitoring them, and we'll have a chance to ask Carla these questions at the end of the presentation. So without further ado, let's all give a warm virtual welcome to Carla Scaletti.
Thank you, Keith. And thanks for inviting me to be part of the 2021 Splice Institute. So everyone at the Splice Institute already knows what I mean by emergence. It's that strange phenomenon that can happen when you're making music with other people, and it becomes something like a third entity. Something unanticipated emerges from the interaction. But not everyone has had that experience. So I've been experimenting with ways of giving the audience a chance to be part of making the music in some of my pieces. I noticed, at least for myself, that I also listen differently when making music than when sitting passively in a concert. So I thought the audience might listen differently if they knew they were generating and influencing the sound. And I was curious whether that different kind of listening might even carry over into the other pieces that came later in the program. Plus, it seems like we're constantly being trained not to listen because music is almost always playing in the background. If you go to a bar or a club, people always seem to be shouting to each other to be heard over the music as if it were noise. So part of the experiment was to try to counteract that pressure not to listen. The general setup for these pieces is that there are microphones surrounding the audience, and audio from the microphones influences a model of some dynamical system running in Kyma, which then captures and processes the audio input, and also synthesizes sounds influenced by the input and sends a resulting mix of composition and sounds to the speakers surrounding the audience. For example, in autocatalysis, the audience had little clickers that they could use to influence two coupled brusellator systems, and it depended on amplitude and things like position in the room. For odd kind of sympathy, the audience has tiny brass bells with different frequencies that they can use to kick oscillators into sync and influence a Kyma model based on a pendulum clock escapement. And in double well, people use toy flutes to drive the input to a model of a double well potential. At various times during the piece, the audience is asked in a humorous way to do things like try to synchronize their breathing, or everyone now converge on the same pitch, or synchronize with each other rhythmically and then speed up together, which turns out they can do surprisingly well. And since the flutes and bells and clickers all have a lot of high frequency content, it's easy to use like 96 kilohertz sample rate and a high pass filter to filter out laughter while still preserving the upper partials of the toy instruments. In preparing for these pieces, I asked myself, what are the conditions that can result in the spontaneous emergence of sync and other kinds of patterns in groups of individuals? And the next 3 video clips are the beginning of an answer to that question. So this is a clip from Nat Geo Wild, showing fire ants responding to a flood. They use the larvae as flotation devices on the bottom, and they stuff the queen into the center and link their legs and mouths together, forming a raft. A raft can survive in the water for several weeks or until they reach dry land and crawl out. This is an example of John Conway's game of life. It's a 2D grid where the on-off state of each cell depends only on the state of that cell and its neighbors in the previous generation. Conway offered a reward to the first person who could come up with an infinitely growing pattern. And another mathematician named Bill Gosper won the prize when he came up with the glider gun. So this is an even better one called Gosper's breeder that keeps resupplying the glider guns and grows exponentially. The glider guns are on the left, shooting out diagonal streams of dots called gliders. And the big guys swimming toward the right are called puffers. And when it zooms in, you can see that when the debris left by the upper and lower puffers meets in the center, it forms a new glider gun that starts shooting out more gliders. So it's an infinitely growing pattern that grows at an exponential rate. So, if anyone had a cup of tea or coffee today, I can't see your reaction, but maybe some of you had some coffee. And you know that nice effect, like if you pour milk into coffee, just watching it slowly diffuse and change color from the deep brown to a more milky color. So then imagine that instead you poured the milk into your coffee and then you saw it start oscillating between brown and white over and over again. That's along the lines of what happened to the Russian biochemist Boris Belousov when he was trying to mimic a biochemical process called glycolysis. To his amazement, he saw a chemical reaction similar to this one, a reaction that was oscillating and cycling between different colors. He tried to publish his results in 1951, but the reviewers rejected the paper, saying that was impossible because it violates the second law of thermodynamics, which basically says that entropy is always increasing, going from more ordered to a less ordered state, like the way milk disperses through the coffee, and you can't reverse the process and pull the milk back out of the coffee again. But it turns out Belousov was correct, and the second law of thermodynamics is also correct, because the second law of thermodynamics is talking only about the endpoints, the equilibrium states. It doesn't say anything about how you get between the equilibrium points. And Belousov's mixture does reach an equilibrium eventually, because the oscillators slowly die out. It just takes a long and winding road to get to that point. As composers and performers, we tend to be interested not just in the beginning and the end, but in how to get from one point to the other. For us, it's the dynamics, the temporal patterns and the way things evolve in time that are at least as interesting as the final state, if not more so. And it turns out there's an entire field devoted to the study of the way things change over time called dynamics, the study of systems that evolve over time. So you probably noticed a few things that all three videos had in common. First, they're all dynamic. The interesting patterns we see are temporal patterns that evolve over time. That's why you needed a video to see it. Secondly, the patterns form at a macro or global level. They span multiple individual lower level components to form a higher level entity, like when the individual ants form a big raft, or the individual cells in the game of life form a glider gun animation, or when the relative concentrations of different kinds of molecules in the glass beaker change the color of the solution. And third, in all of these examples, the pattern is in some sense unexpected or unanticipated, in the sense that if you were to examine a single component in isolation, there's no way you would predict that the low-level component could generate the higher-level behavior. If you took an ant, an isolated ant, and asked it how to build a raft, it's unlikely the ant would know how to do it. In the game of life, an individual cell is only on or off, just black or white. So looking at one cell, you wouldn't expect it to be able to generate an animated glider gun. If you added only one of the chemicals from the Briggs-Rauscher reaction, it would no longer oscillate, it would just irreversibly dissolve into the mixture like milk does into the cup of coffee. In all of these examples, the potential for generating the pattern is not solely in each individual, but in the way the individual components are connected to one another. In all cases, there are simple local interaction rules that, when taken in combination, result in some surprising large-scale behavior. Each ant is reacting to the flood according to a simple rule, like lock your mouth onto another ant's legs, or pick up a larva and move it to the bottom of a pile. These actions individually don't form a raft. It's only when they're done in combination with a large number of other ants that it forms the global pattern. To get a chemical oscillator, you have to have two competing reactions, pulling the concentration one way and then another. First, an autocatalytic process that explodes until it uses up all the raw materials, combined with a competing process that feeds on the materials the first one produces, while itself producing more raw materials for the first reaction, so it can explode again later. So that's why they oscillate back and forth. These three attributes are part of the definition of the word emergence. An emergent entity is categorized or characterized by its constituent parts, and by the way the parts interact with each other. The rules specifying the interactions are relatively simple and local. They don't refer to the large global pattern. Emergent properties or patterns or behaviors are those that could not have been foreseen solely by examining the constituent parts in isolation. Do the emergent entities really exist? Or are we just perceiving a pattern that isn't really there? I mean, the glider guns in the game of life aren't really guns shooting out gliders. On the other hand, they are a vivid demonstration of how aggregations of simple initial conditions and combination rules can result in complex patterns in time and space. So we could view the game of life as a simulation of how emergence could arise in the physical world. The ant raft, on the other hand, is a real phenomenon, and it serves a real function by saving the ant colony in a flood. Likewise, the chemical oscillators are a real physical phenomenon. So if you've ever attended a remote event like this and you're in a different time zone, or if you've ever experienced jet lag, you know firsthand that there are biochemical oscillators in our cells that help control the circadian clock and the sleep-wake cycle. As part of the background research for the pieces, I looked at Stephen Strogatz's books about the spontaneous emergence of sync and about dynamical systems, and then started experimenting with using dynamical systems to generate sound and also to control sound parameters. For example, here is a dynamical system that has two dimensions, two state variables, meaning that in order to predict how the swing is going to move, you have to know two things, its angle and its velocity. For example, you could be at exactly the same position, the bottom of the swing, and either be at maximum velocity if you're on the way up, or at zero velocity because you've completely run out of steam. If someone comes along and gives you a push, then it becomes a forced or driven system, which makes it more complicated. It's kind of like adding a third variable. Strogatz gives an overview of dynamical systems where he has the horizontal axis showing the number of variables, or the number of dimensions needed to represent the state of the system. And he lists those as 1, 2, 3, a whole bunch, or infinite. On the vertical axis, he has linear systems at the bottom, or sorry, linear systems are at the top and nonlinear systems are at the bottom. So at the upper left, you see simple dynamical systems that exhibit growth, decay, and equilibrium for a single variable, or oscillations when you have two variables. In the lower left, the nonlinear part, you start to see fixed points and bifurcations for one-dimensional systems. And with two variables, you can get nonlinear oscillations and biological oscillators like neurons and heart cells. With three variables, you first start to see chaos and strange attractors, which some people consider to be emergent properties. Inside the shaded area are the topics that Strogatz considers to be at the frontiers of complexity science. So if you're looking for a good PhD topic, maybe this is a good place to look. This is where he lists topics like coupled nonlinear oscillators, neural networks, the immune system, the ecosystem, and the economy. And in the far lower right corner, he has an intriguing topic that just says life. What if we wanted to create some sonic emergence? What are the conditions we would have to have in order to make it possible for emergence to arise? I tried to piece together what Strogatz and others had to say about the ingredients you need in order to cook up some emergence. We know we need a collection of objects that interact with each other according to simple local rules, and that these interactions should be based on shared information as opposed to coming from a central leader or a global coordinator. And that we want the whole system to be dynamic or time dependent. In other words, we want the current state of the system to be a function of its previous state, which is another way to describe, or another way to describe that is feedback. Something we're all very familiar with in live performance with electronics. It's where you take a live microphone and hold it directly up to the speaker. And the output of the system gets added to the input, which affects the output, and so on. According to Strogatz, we need at least 3 dimensions to represent the state of the system, 3 variables, before we start to see emergence in the form of strange attractors. And according to everything I've read, there should also be nonlinearity. And by nonlinear, I mean the whole is not just the sum of the parts. If you're running a zoo and you know how much the lamb eats and how much the lion eats, and you put them together in a cage, you might expect that you would have to supply that cage with the sum of what the lamb and the lion eat. But that may not be true if the lion and the lamb somehow interact with each other. So let's try it. Let's try to build some systems in Kyma that might demonstrate emergent behavior. Let's start with a one variable system with feedback. Usually when you move a fader, you're saying, here's a new value of X, jump to that value. We could instead make a different kind of fader where we're saying, here's a new value of X, start where you are, start at the current value of X, and take a small step in the direction of the new value. So over here on the lower left, we have the current value of X, and directly above that is the new target value called reference. First, let's compute how far away they are from each other, how far the X is from the target, by looking at the difference between the current value of X and the target value. And to control how quickly we would move to the target value, multiply the difference by a fader K. So for large values of K, the value will change quickly, and for small values, it changes more slowly. Then use this mixer to add a little bit of that change to the current value of X, so it takes a tiny step in that direction. And then the feedback. This is where we would feed back the new value, the new position of X, and compute a new difference between the reference and the new position of X, and so on. As x gets closer to the reference value, this difference gets smaller and smaller. So we're adding smaller and smaller increments to x as we get closer and closer to the target. So now if I move the reference to a new target value, x starts from the current position and moves toward the new value. When k is large, you take big steps toward the new value, so it gets there faster. And when k is small, you take small steps, and it takes a longer time to reach the reference value. So with just one variable in feedback, we can get exponential growth and decay. If we introduce two variables, we can make an oscillator, because now the two equations can fight each other, one pulling up and one pulling down, to create this oscillation. This is a van der Pol oscillator. It has two variables, x and y, plus another ingredient required by emergence, nonlinearity, that x cubed term. This is a model of a vacuum tube oscillator that the Dutch physicist Balthasar van der Pol came up with in the 1920s when he was working at Philips. You can control how nonlinear it is with this control parameter mu. When mu is 0, you're multiplying the nonlinear part by 0. So the nonlinear part just goes away, and you're left with a simple harmonic oscillator. But when mu is larger than 0, the van der Pol oscillator has this really cool property. No matter what its initial state, the oscillator always moves toward a fixed amplitude, which is the square root of 3. When the amplitude x is larger than that, the nonlinear part is positive. So when you subtract it, it acts like a damping factor to decrease the amplitude. If the amplitude is smaller than that, the nonlinear part is negative. So when you subtract it, it acts like it's adding, and it acts like a pumping factor to increase the amplitude. So a van der Pol oscillator always moves to the same fixed amplitude. So here we're looking at x versus y, and the button in the upper right corner injects random initial points and then starts computing. And m is the mu. I just called it m in there instead of mu. When m is 0, each initial point turns into a harmonic oscillator, at each one at a different amplitude. So in this space, a harmonic oscillator is going to look like a circle. So I'll try to inject. Okay, so they're oscillating. Now, if I introduce just a little bit of nonlinearity, the low amplitude oscillators near the center spiral out to a large amplitude, larger, and the large amplitude oscillators outside spiral in to the same amplitude. So no matter what the initial points are, they spiral in or out to that one amplitude in the middle. That's called the limit cycle. As you increase the nonlinearity even more, it becomes what's called a relaxation oscillator, where it slowly builds up tension and then suddenly releases it to jump to the other side. These kinds of oscillators are sometimes used for modeling biological oscillators like neurons, or to model the buildup and release of stress in an earthquake. Strogatz says you need 3 variables, though, to get to the strange attractors and chaos. So let's look at the classic 3-dimensional nonlinear system called the Lorentz equations. In 1963, Ed Lorenz was an MIT meteorologist who came up with a simplified model for convection in the atmosphere. That's where hot air rises, and then at high altitudes it cools off and starts falling, and this sometimes creates these convection rolls like you see reflected in the clouds there. Lorenz noticed that when a control parameter representing instability due to temperature and density was set above a certain value, he started to see strange behavior. So here's the 3-dimensional Lorentz system in Kyma. The red points are at different initial states, and the trajectories look as if they might be going into a limit cycle like the van der Pol oscillator, but then unpredictably a point will seemingly decide to take the upper loop instead of the lower loop. And even the points that started out really close together at the beginning diverge exponentially over time. Lorenz tried to analyze the long-term behavior of a system and found what seemed like a paradox. There were no stable fixed points or limit cycles, but all the trajectories were eventually attracted into a bounded region of the state space, what people now describe as chaotic motion and a strange attractor. Philosopher David Newman argues that strange attractors are authentic examples of emergent phenomena, because although something like a chaotic fluid flow is completely deterministic, in order to predict its future states, you would have to know its current state to infinite precision, and that's impossible. Every state measurement has some error in it, and as Lorenz observed, all those errors increase exponentially over time, so there's a very sensitive dependence on initial conditions. Another way to put this is, the only way to know the future state of a chaotic system is to actually let it play and observe it. Strogatz, on the very last page of his book, in almost the last sentence, writes, as soon as we consider forced oscillators and other non-autonomous systems, strange attractors start turning up everywhere. And then the book is over. It's almost like it was a big tease for his next book or something. Anyway, let's try that next. Let's try starting with a two-dimensional system and adding a driver to it. Adding a driver to a system is like coming up to a dog sitting passively in a swing and giving him a periodic push, not necessarily in sync with the swing's natural frequency. But instead of a dog on a pendulum system, we can start with a two-dimensional nonlinear system in Kyma, the van der Pol oscillator. And let's give it a periodic push with a sine wave oscillator input. So here, the van der Pol relaxation oscillator is being driven by a sine wave oscillator. So now, instead of getting that nice, stable limit cycle like we did before, we see a lot more wandering around. The points are taking lots of alternative swirly paths, and they don't always take the same paths. There still seems to be a bounded region where the points are moving, but instead of all lining up to draw the same circle, they seem to be taking lots of different paths through the space and drawing like what to me looks kind of like a Santa Claus face. So that's what happens when you use a totally arbitrary driver, a simple sine wave oscillator. What if instead we use the driver as a way of sharing information among the points? In other words, what if we use the driver as a kind of a signaling pathway among multiple dynamical systems? That would get us a tiny bit closer to the idea of ants in the flood, because it would be a system of multiple individuals connected in a network. For example, what if we start with a bunch of relaxation oscillators and give each oscillator just enough of a brain to make it aware of its own position relative to the positions of its friends? We could use the driving function input to each oscillator for sharing that information. And we could give each oscillator a simple rule, which is try to stay in the middle of the pack. Or in other words, slow down if you're getting ahead of everyone else, speed up if you're falling behind. So imagine these relaxation oscillators running around a kind of oddly shaped track, totally oblivious of one another. At the bottom, you can see their angles are all independent of one another. To increase their awareness of each other, increase the fader on the right, called coupling. That makes them aware of each other, or at least aware of how different their position is from the other positions. If they're going faster, they try to slow down for the others to catch up. If they're going slower, they try to speed up. Some of them even try to cheat by cutting across the center of the track to catch up. When I decrease the amplitude of the driver by reducing the coupling fader, they don't care about each other anymore and they start splitting apart again. But if you restore the strength of the coupling, they'll synchronize again. where they're all drifting apart. Now I'm going to set it to a high coupling again. And they quickly come into sync again. So finally, with this last example, we created a simple example of emergence using Kyma sounds. A network of nonlinear oscillators that by communicating only with each other, were able to achieve global synchronization, even in the absence of a central controller. And it's at least somewhat surprising or unanticipated, although probably not to you guys, because musicians are routinely able to synchronize with each other, even in the absence of a central conductor. But that too is an example of emergence. If you look up in Google spontaneous emergence of synchronization, you find some pretty interesting results. In this context, spontaneous means that it occurs without a central or global control source. So it fits with our definition of emergence. It's a global phenomenon that arises due to the way multiple individuals are connected, and it happens without a central coordinator. And it can happen without the individuals necessarily even being aware that it's happening. The spontaneous emergence of sync among relaxation oscillators is especially relevant to us as biological systems because it's been observed in ensembles of heart cells, in groups of neurons firing synchronously in the brain, in gene regulation networks and DNA repair, and in larger scale actions like breathing or being able to coordinate your limbs for running and walking. Apparently, it's even possible for two individuals' brains to synchronize with each other. In this study called How Two Brains Make One Synchronized Mind in the Inferior Frontal Cortex, the researchers monitored the brains of two people while they were singing or humming together. During cooperative singing or humming, they found significant increase in neural synchronization in a part of the brain called the inferior frontal cortex. And this was true whether the singers were looking at each other or whether there was a screen placed between them. So the brain synchronization really seemed to be due to the audio synchronization, or vice versa. Once you start thinking this way, looking at large ensembles of individual actors, noticing how their interconnections and the simple rules governing their interaction are at least as powerful as the characteristics of each individual, then you start seeing emergent behavior everywhere, from traffic jams to market crashes to the weather. There are even those who argue that the mind is an emergent property of the physical brain, or that space itself is an emergent property of a large number of elements interacting with each other according to relatively simple physical laws. That's the conclusion that Stephen Wolfram arrives at in his book, A New Kind of Science. Wolfram writes, over and over again, we will see the same kind of thing, that even though the underlying rules for a system are simple, and even though the system is started from simple initial conditions, the behavior the system shows can nevertheless be highly complex. Wolfram argues that it's this basic phenomenon that is ultimately responsible for most of the complexity we see in nature. And because Wolfram suspects that the universe is discrete rather than continuous, he models the universe using discrete systems called cellular automata, systems that are very closely related to the game of life we saw in that second video clip. In these photos, Wolfram shows some startling similarities between the patterns on mollusk shells and the outputs of various one-dimensional cellular automata. One-dimensional cellular automata are like the game of life that we looked at earlier, except they're even simpler. A one-dimensional cellular automaton is an array of cells. The state of each cell depends only on the states of its two neighbors and itself in the previous generation. The rule for combining the three states can be encoded by a single integer. For example, rule 110. Here's the pattern that's generated by rule 110. Wolfram had suspected this for a long time, and his research assistant, Matthew Cook, was finally able to prove that the automaton rule that's called Rule 110 is equivalent to a universal Turing machine, meaning that this simple 1D cellular automaton can emulate any program. It can compute any algorithm. It's a little bit astounding that something with such simple rules and initial conditions could be computationally equivalent to the most powerful supercomputer. It makes you think that maybe there really could be systems in nature that are capable of computing. Cook said something else interesting about Rule 110 in his paper, that many questions concerning its behavior, such as whether a particular sequence of bits will occur or whether the behavior will become periodic, are undecidable. In other words, that it's impossible to construct an algorithm that would answer those questions. For example, take an elementary cellular automaton like Rule 250, shown on the left. Look at the white cell where the red arrow is pointing in the 16th generation and ask yourself, what will the state of that cell be 1 generation from now? You know the answer, black. How about 2 generations from now? White. 200,000 generations from now, it will be white again. So you're able to reduce that cellular automaton's rule to something much simpler, just an even-odd test. But Cook and Wolfram are saying that for Rule 110, shown on the right, there is no way to predict what that cell will be 200,000 generations from now. Because Rule 110 is equivalent to a universal Turing machine, any algorithm we might come up with for predicting its behavior will be equivalent in complexity to Rule 110 itself. So the only way to find out the answer to the question is to run the automaton. Wolfram calls this the principle of computational equivalence. If a system you're trying to do prediction on is equivalent in complexity to the tools you have for understanding it, whether that tool is your brain or mathematics or a computer, then for such a system, the only way to predict its outcome is to actually run it. There's no way to reduce it. You just have to take the time to simulate it and wait and observe the behavior when it happens, which may be another way of saying that the system's outcome is emergent because we can't predict it, only observe it. Wolfram concludes by proposing that the entire universe is doing computation, that, quote, all processes, whether they're produced by human effort or occur spontaneously in nature, can be viewed as computations. In our everyday experience with computers, we think of computation as performing a specific task, but computation encompasses more than that. For example, the evolution of a cellular automaton can be viewed as computation, even if the only result of that computation is the pattern of white and black squares that it leaves as a trace. In other words, you can do computation with more than just numbers. The way Wolfram puts it, we see computations being done with a vast range of different kinds of data, from numbers to text to images to almost anything else. And what this suggests is that it is possible to think of any process that follows definite rules as being a computation, regardless of the kinds of elements it involves. When I read that statement, it's possible to think of any process that follows definite rules as being a computation. The first thing that comes to mind is music composition and live performance. Could it be that by designing sounds and composing music, we're performing some kind of computation? Is it possible that we and the ants and our music and our DNA and the universe are all computing? And that when we use laptops to actually find an answer or generate a sound, we're just taking a subset of that computation and harnessing it and guiding it to our specific purpose. If ants can build a raft without understanding or even realizing what they're doing, Is it possible that we too are working on a project so much larger than ourselves that we can't even comprehend it? And that maybe the music and sound we feel so driven to create is not just an idle entertainment, but an essential part of a larger computation. I was thinking about the Splice Institute, and I realized that we're a bunch of loosely coupled individuals. And the rules of interaction at Splice are pretty simple. We're just sharing information with each other, listening to each other, reacting to each other, giving feedback to each other, performing and working together in nonlinear combinations. It seems like all the necessary conditions are in place to generate some unanticipated emergent phenomena. So thank you for inviting me to be part of it. I can't wait to hear what's going to be happening this week. The end.
Thank you, Carla, for that wonderful presentation. I do have a couple of questions from our audience. There were two questions that were asked when you were discussing the spontaneous emergence of sync.
Okay.
Michael Broder asked if the coupling applied to each particle equally. And Adam Vidixis asked, does the coupling always inevitably lead to synchronization where greater strength leads to shorter times? Or is there a threshold above where this occurs and below which, but greater than zero, it doesn't?
So each particle or each oscillator was getting the information about where it was relative to the others, and the rule was that it would try to adjust to be in the middle. So with a different rule, I don't think you would get synchronization. I think it's kind of like whenever you're doing the game of clapping and try to synchronize with each other, subconsciously you are adapting, like you hear what's going on and you might speed up a little bit, you might slow down a little bit, like you're doing this little adaptation. So that part of the rule has to be there, I think, in order to make it synchronize. I don't know about having too much. Yeah, good question. Having too much of it probably would push it into some other behavior, but I mean, I suspect that it would just clip, but I would have to try that. I don't know for sure.
Thank you for those. Any other questions from anyone out in the audience? You are getting a ton of thunderous applause, by the way.
Thank you.
Wonderful comments. Mind blown from Carla. My head's in a good way, says Brian Belay. So lots of wonderful things. I'll give it a second, see if there's any other questions that come in.
Have you experienced emergence when you're performing with other people? I'll ask you the question.
Oh dear. I think so. I think it's, I mean, I think a huge part about performance is is the unexpected, and and I like the idea that you proposed, that we're all part of a wider whole contributing to something that might be much bigger than we're even aware of, like the ants with the raft. I think that's a neat idea that really frames it outside of ourselves and outside of the hall. I like that a lot.
I mean, it feels like there must be some reason, because we're driven, right? It's not just a casual thing. Like, we're kind of driven to keep doing this, and
yes,
it's hard to know why. Maybe there is a reason.
Maybe we're just ants.
Maybe we're building a raft.
One last question. Christopher Biggs asks, what is the best place to check out more of your work?
Oh, thanks. CarlaScaletti.com is where I put links. Of course, it's not up to date, but I will work on it, work in progress, as all websites are. But it's just myname.com.
Oh, actually, we do have a couple more questions now after that. So Patrick McGraw asks if you think that Terry Riley's In C is based on emergence.
Huh. I don't know if it's based on it, but yes, I think that there is emergence in that piece. Yes, because there are things that you wouldn't anticipate with this simple repetition and looping. You wouldn't expect some of the patterns that you hear. So yeah, good call.
And Connor Scroggins and Per Bloland both ask kind of similar questions. Connor asks, how do you experience emergence while composing a work? And Per asks, says he'd be interested in hearing how you apply these principles to your work.
So yeah, I think the emergence might be one of these real-time experiences rather than, like, for me, composing is iterative and not real-time. The closest I would say that I would come to that is this idea of flow, maybe, that when you're first starting on a piece, it is kind of sometimes really painful because you're just not seeing where it's going, or you start out one way and then it's not working, and then at some point it feels like there's all these pieces that come together, and then suddenly it's fun. Yeah, so I guess that maybe is emergence, because it's like all these different pieces that yeah, that you wouldn't think of. Maybe usually also there is a point in a composition where there are some unanticipated directions. Like I almost always think I'm going to write this piece, and then when I start on it, I'm fighting with it, and suddenly it's going in a different direction, and I realize, oh, okay, so yeah, probably I just changed course midstream there, just like I would when I'm composing. That yes, good. That's a good point. That's how I would see emergence happening there.
And one last question from Mark Sullivan, who asks, what happens if you create a structural coupling between two distinct emergent systems?
Whoa. I think unanticipated. I don't know. I think it's one of those things that you would have to build and let it run in order to hear what happens. I think it's too complex. I mean, it has the computational complexity issue that you wouldn't be able to predict. So Mark, you should try it.
Well, again, I want to say thank you so much for this talk, and also just for being here this week.
Thank you for the
and just
invitation.
sharing all of this with us. So thank you so much. Again, everyone, give a virtual applause to Carla, and please return at 7:30, our same YouTube channel. We will be kicking off our concerts, our weekly concerts, starting with our featured guest ensemble, Pope Bama. So that'll be 7:30 back here on YouTube. So again, thank you, Carla, so very, very much.
Thank you. I'm having a lot of fun here. Thank you.